We've got a homework due today, and it is homework number 8, I think, and it's on socket programming. And I think we've covered it pretty thoroughly, and I could tell from how people had submitted that a number of people have already submitted the homework. So it looks like we're ready to move on to bigger and better things. And what I'll do is I'll call this homework, unless there are some questions on the homework. Are there any questions on the homework? Try to insert a new slide here. Hearing none, this will be my introduction to multicast programming. And that is a UDP IP approach. So we're going to use IP, the Internet Protocol, but we're not going to do TCP IP. We're going to do UDP IP. And so we had a brief discussion about that last time, but we haven't really gotten into any of the nitty-gritty details of why you would do such a thing and how such a thing might work. So without further ado, let's see if I can get this to go up full screen. That's cool. And so first thing is what's a multicast socket? And we've seen TCP IP. That's unicast. So that's a point-to-point connection, which is reliable. The data that goes in one end comes out the other end. So it's a pipe, just a bit pipe. It handles streams. I'm going to call on people because I find it a little difficult to have these lectures without any feedback. And so I'm going to go in alphabetic order. Angelica, what's a stream? That's Angelica McAfee. I think I pronounced your name properly. What's a stream? So a TCP IP uses streams on a bit pipe. What's a stream? How about anybody else? Anybody want to venture a guess as to what a stream is?
I think it's just like a sequence of data.
That's exactly right. It's an unformatted sequence of bytes is what it is. And we don't know what's in the stream. Could be images, could be audio, could be payroll. Don't know. But we know it's an unformatted sequence of bytes. But UDP is different. UDP uses packets of data. So that is just like a little letter. You create a data structure, you put the packet of data in it, and then you send it off. And there's no acknowledgement necessarily built into the protocol. So no acknowledgement. Unless you want to put it in to a layer above the UDP system, which you can do. That's a perfectly legitimate thing to do. In fact, it may even be a desirable thing to do. So unicast versus multicast, how does it all work? With unicast, we have a one-to-one mapping, known in the mathematics biz as an isomorphic mapping. And so what happens is every sender has to have a receiver, and in principle, you're duplicating the data for each receiver. And that's not necessarily desirable. And that's unicast protocol. If you want to achieve a group communication, then you want to use multicast. And what that is like it's a broadcast. So if you're trying to do a zero network administration overhead plug-and-play device like a printer. You plug it into the network, and it says, are there any domain servers in this network neighborhood? And somebody will respond and say, yes, here I am. What do you want? And it'll come back in its normal protocol, dynamic host control protocol, and said, I need an IP address. And some host server will say, okay, here's one. And now that you've got one, using unicast response, what else do you need? And it comes back and says, well, I'm a printer and I need to be listed. So the domain controller then lists that printer so you can find it in your network neighborhood. That's a typical sort of Windows back and forth. So why don't we all use multicast sockets? And the answer, of course, is not all routers will pass them. And those that do won't allow them to go and spread indefinitely, because if they did, you would flood the internet with your multicast packets, and that wouldn't be good. So we have a TTL, a time to live, and that is equal to the maximum number of routers a packet can be permitted to cross before it is blocked. And so you usually have that limited at about 3, perhaps up to 6, and then at the end of the day, it's done. And when you establish your routers to pass those multicast packets, you're establishing what's called the M-bone, or multicast backbone. So why do I need it? And well, I gave the example of the plug-and-play printer. It allows for discovery. It's very good for broadcast of multimedia data. And there is a device, which many of you may have actually, called the ether switch, which does a kind of routing that protects legs from traffic, but will pass multicast packets. So that's kind of nice. You don't need a router to have multicast capable local area networks. Your ether switch will do it. There's also another kind of switch called a dumb switch, or it's a hub, an Ethernet hub, not a switch. And all it does is replicate the electronic power needed to drive the next line over, or the next leg of the Ethernet in a local area network. Ether switches are often configured in a star topology. And so you could have one with many legs go into another one with many legs. And so that enables you to kind of branch out the network and extend it. But usually with ether switches, you would be limited to perhaps an absolute maximum of 255 nodes, actually less than that. There's also limits on the total length of the cable, but those physical limits are not a part of the standard. It's part of a different standard, physical layer standard. So IP multicast, it's an interesting service model. First of all, it started in 1989 with a request for comment. So it's been around for a while. People use these datagrams. I called them packets before, but datagrams is just as good. You might call them either. I don't know. Sometimes people will interchange the nomenclature on this. And then that goes to a group, and sometimes it's a promiscuous transmission, so it can be sent to some non-selective group, basically everyone. The members of this group can be present anywhere in the internet, but they may not receive the packets if the time to live is too short to reach them. Members can join and leave the group. That's good because they may or may not want to listen to all this broadcasting traffic. And then this can be indicated to routers. So when you join a group, the router finds out and it can multicast route the packets or datagrams off to that receiver. So senders and receivers are distinct, typically different, although a sender can receive their own multicast packets. You can enable it, but usually a sender isn't in a position to receive its own multicast packets until you override the default. normally when you're sending out multicast packets, you're not receiving them too, at least not in your own channel. Our routers listen to all multicast addresses and use the multicast routing protocols to manage the groups. So routers are group aware if they're multicast aware. Not all routers are multicast aware. So a multicast group address is really just like a TCP IP address with a difference. And the difference is the high order bits. It's a class D address. And so what you're dealing with is 224.0.0.0 all the way up to 239.255.255. That's a lot of addresses. Each one of these is 8 bits. And then this is representing a high order 3 bits. So if you think about it that way, it's 16, 24, 25, 26, 27 bits worth of address space, which is a big honking number, actually. And so there have been very well-known addresses already reserved, and you can use some of these if you don't mind clobbering somebody else's multicast address. So if I start sending out packets with these addresses, they are multicast addresses. And so what I get to do as a programmer is I get to figure out where my multicast packet is going and to who, and then I can assign to that multicast packet not just an address, but a group. And if I want to, I can just send it out to the group, and everybody in the group should be able to receive it. So I take the lower 23 bits of the multicast class D address, and I insert it into the MAC address. The MAC address is the media access control sublayer within the data link layer. So how does it work? The MAC address is assigned to every node on an Ethernet network. So if I have a Mac, and I do, and I say ifconfig, I should be able to find the MAC address. And in fact, if I pipe it into grep on Mac and then pipe it into more, well, I might be wrong about that. Let's uppercase it. I'll try again. Somewhere in here, we should find MAC addresses. And here's one. They just call it Ether. For some reason, I thought it was called Mac. So this would be a unique hardware name that's associated with the Ethernet chip that's in the computer. So this is a hardware address. So where is that? Well, there's the physical layer. That's the Ethernet. But then there's the data link layer, and then there's a routing layer on top of that, the network layer. This is in the sublayer between, hello? This is in the sublayer between the IP address and the data link layer. And we can see there's another MAC address over in here, but this one is associated with my IP address. I'm starting with a 192 here because I'm a non-routable or private address. In order to get through, to me, I use network address translation in my router, and that will allow my router to appear as though it has an IP address that's public. So in other words, if I go to something like what's my IP address to the outside world, I'm seen as here. But because my router is not routing packets to anywhere inside of my network, in general, you can't get in, but I can get out. that makes sense. You'd have a different MAC address for your Wi-Fi. So if I turn Wi-Fi on, then I would have another MAC address associated, but also another IP address too. So multicast announcements are sort of interesting in terms of the protocol that they use. They have a port associated with them, just like TCP/IP. They've got an IP address, just like TCP/IP, but they're sending out datagrams, UDP datagrams, and here comes a lookup server, which makes an announcement sent via UDP multicast, and port 4160 is apparently being listened to by the discoverer for this multicast address. So they give a request message to the lookup server, and they can do that using UDP or, in this case, TCP. So that's a unicast response to a multicast announcement. So the lookup server can make a multicast announcement that says something like, everybody re-register your IP addresses. And so here, this fellow, the discoverer, comes back and says, okay, I'm going to reply to you with a unicast response on a specific port number and ask you for a new address. And then your response comes back and says, via unicast, TCP/IP, here's your new address, and don't bother me again. And so there. So here's another lookup service. And we can sort of see how interactions through various protocols can occur. Here we'll do the client doing a lookup service query. And the lookup service query might say, I'm trying to find a compute server. And the lookup service registers compute servers. So it says, you know, I got one over here. Here's a proxy with an IP address. Somebody's not busy, a compute server you can use. So now the client can go and interact with the service and say, okay, here's the service object. Go compute this. Here are the attributes. This is what you need to know. And then somewhere down the line, after it's computed, it's returned to the client. So at some level, one could make a compelling argument that you have an architecture based in the network for doing distributed computing. And that distributed computing, because it occurs on different computers, is truly concurrent computing. This is not like multitasking. This is multi-computing. So that's an interesting way in which to approach the distributed computing problem, right? The lookup server can organize all of the machines which are on the network and can help you to identify them in terms of when they are available, but that is when they're idle. So now I've got an opportunity to take some sort of data and distribute it across different nodes. And the nodes can help me to distribute to other nodes. I could have various lookup servers along the way. And that's kind of interesting. So I could have a whole network of lookup servers, and they can work at local area network areas that are, I will call them geographically co-located. So for example, let's assume that I have a lookup server at Fairfield University, which keeps track of everyone who's running my screensaver. Whenever somebody's running the screensaver, I assume the computer is idle. That could be like a lot of computers right now because a lot of people are on lockdown. So as a result, I could have access to a lot of different computers in the Fairfield University lookup server. And then I contact the lookup server, and it can use multicast to let servers know that it's available for them to register with. And moreover, it can contact another lookup server somewhere else on the network, the internet, and say, hey, I'm a lookup server with access to 1,000 machines, which is cool. So now let's assume for the moment that there's another campus somewhere, University of New Haven, and they have a lookup server. So now that can also register all its geographically co-located compute servers, and then register that back to lookup server central, wherever that may be, Doc Java Incorporated World Headquarters. So at some level, one could make a compelling argument that you could have a virtual world compute center, right? It just goes and organizes all the compute services that are idle on the planet and turns them into a ginormous supercomputer, provided you can take the tasks and divvy it up amongst the computers. So one could make a compelling argument that because this is a connectionless protocol, it is an unreliable one. You're taking datagrams. Here it's called packets. Never to exceed 512 bytes. That's not much. And if you have longer files than 512 bytes, and you almost certainly do, then you've got to break it up into multiple packets. And if somehow you want those files to be intact upon arrival, the receiver is going to have to assemble those packets. And if some of the packets are missing, the receiver is going to have to keep track of the packets and go back to the transmitter and say, never got it. Got to send the packet again, because, or resend the packet that we're missing, and assemble things over time until you have all the packets you need. So if you have an Ether switch, and these are probably the cheapest of network appliances, even at speed, I think they're terribly inexpensive. In fact, we could take a quick look just to sort of see. I don't think you have to spend more than $30 to get a good Ether switch nowadays. Amazon is probably a logical place to look for an Ether switch. And here they are for $18. And that's a gigabit Ether switch. Unmanaged. Will pass multicast. Comes into the metal housing too, so that's cool. It might be a little hot, but the metal housing will keep it cool. I bought a bunch of these actually, Netgear, and TrendNet has these too. The TP links, $16.99. I mean, these are not expensive network appliances. So when we look at this, here's one for $9.99. Wow. Okay. So you get the point. You plug these in, you can extend your network, and they're unmanaged, so they're not going to isolate traffic except for traffic that's not intended for another leg, and that'll only be the unicast traffic. Multicast traffic is just going to pass right on through. And that's anything with the designated IP address. And yes, you can get them at 10 gigabits per second, but I don't do that because, well, my computers don't go that fast. Maybe your computers do, but mine do not. And also my network is rather more limited. My connection to the network is perhaps only 300 or 400 megabits per second, which is considered fast nowadays, I guess. So that's an enabling technology. And now we can do video on the Ethernet, and that used to be a big deal. Couldn't do that before. So now everybody's cutting the cable and moving to, I don't know, whatever, Amazon Prime or Netflix or YouTube or something. So then there's this standard video, which is sometimes called 720p. It's 720 by 480 pixels at 16 bits per pixel element and at 30 frames per second. Uncompressed, it's 160 megabits per second. But you can do better when you do the compression, and almost everybody transmits this stuff compressed. And that's not a particularly high resolution, because right now I'm transmitting to you in HD TV and 16:9 aspect ratio. But check it out. This is like a large area of white. That's called intra-frame coherence with a little bit of black. There's almost no color in any of this. And whatever the color is, it's constant, except where there's text. So there's a lot of opportunity for compression here. And so when we think about what video is, oftentimes it's image sequences plus audio. So in a sense, I'm transmitting a video to you right now because these is an image sequence of PowerPoint slides and there's a stream of audio. And I can make the image sequences, I can synthesize them on the computer using a screen capture and make things almost noise-free, right? Because if you think about these frames, they are inherently noise-free. There's no, presumably, noise at all. And so the interframe coherence is the difference between frames. The intra-frame coherence is the difference between pixels within a frame. Either can be coded very efficiently because the difference between this frame and the last frame is relatively small, still large areas of white. So we know what the color is. Color hasn't changed, just the sort of the large rectangles have changed. Rectangles of white, you might say. So we look at the Java Net framework, list of classes, well, pertaining to network programming, and we find there's datagram sockets and datagram packets, and this is what we use for UDP. We still need the internet address. We can use multicast sockets and drop the datagram sockets into them. We can have server sockets to listen to these things. And we need URLs and URL connections. So we'll make an instance of a URL, then make an instance of a URL connection from that. That'll give us the ability to drop in our datagrams. So this is a kind of a little list of what you might expect from the internet address. And so there's a mechanism for doing equals, so we can tell if one object is equal to another. And we can redefine how that works if we go from a 4-digit number into a 6-digit number. And then those are hexadecimal digits, by the way. And then the address, we can do a lookup, get all by name or get by name. And presumably we can get the local host. The hash code is for sorting and for, well, for putting things into a efficiently stored data structure, for lack of a better word. And then if you take data structures, you'll know why they have hash codes here. And then if there's anything we can do here to show how internet addresses work, it would probably be just a little piece of code that you would write without too much hurrah. So let's just see if we can get that to work. This is not the way I would have done that. Let's see. I've got book examples from chapter 29. This address resolver should work. And there we go. So apparently google.com has an IP address. This is obtained it using the inet address class. If I click on it, I don't know what happens. Maybe if I use this IP address and then paste it into my browser. Let's go find a browser. Now let's paste that in. What could possibly go wrong? Oh, look, it's Google. So that actually worked. So the resolver essentially performed the function of taking a fully qualified domain name, turning it into an IP address, and then allowing me to print out that address. So that's what that does. That's accessing the DNS, the domain name server, via the inet address class in the java.net API. I think I said that right. So Java has this wonderful multicast API called Multicast Socket. Here I'm able to reverse look up an IP address and get an actual name, and I can define that as my group. I can create a multicast socket with an arbitrary port number and join the group. So that'll give me presumably an IP address with a port, and having that, I can proceed to drop datagrams to that group through that multicast socket. And someone out there is going to try and receive data, and this is going to come in as datagrams. And so presumably we'll have a get data, and it'll turn into a message, and the message will say something like, I don't know, hello world, or whatever the message says. What do messages say? I have no idea. So then to send a datagram, and I'm just showing you this stuff, not expecting you to retain it, but at least you'll have seen it. And if you ever do any serious network programming, you'll actually try it. And so what we'll do is we'll just sort of kind of run through a couple of basic examples so you'll get a feeling for what's going on here. We'll create an instance of the datagram packet, right? So now we have, this is really confounding, right? Before it was a packet, before that it was a datagram, now it's a datagram packet. How's that for confusing nomenclature? Is it a datagram or a packet? It's a datagram packet. And so we're going to take the datagram packet and send it down the datagram socket. And that's going to broadcast it to everybody in the group. If you go to the OSI ISO standard for naming conventions, when you want to send out data at the physical layer, you're not sending bits, you're sending out physical layer data units. That's what they call it. And if you're at the data link layer, you're not sending out packets, you're sending out data link layer data units. No kidding. And then the next layer up, that's the network layer. It's, you guessed it, network layer data units. It is what it is. This is how they name it. So your socket API, which is practically what everybody uses for network programming, the socket API or higher in terms of layers of abstraction. You need your sockets, you need your internet addresses, you have to be able to get input streams and output streams. Your socket will have both an input stream and an output stream. You want to be able to get the port, because that's going to tell you whether or not you're listening to the right sort of phone number, if you like. And you can also convert the whole thing to a string. Everything to string is part of the java.lang.object canonical method set. Every java.lang.object has a toString method. Sometimes the toString method doesn't return anything good. You can override it. So class socket is sometimes just called sockets, and it's an endpoint for communication, and it's meant to set up an unformatted sequence of bytes or a stream. You can open up these connections, but sometimes they don't work, so you can set out the timeout. And if it takes you more than a few seconds to make the connection, you can time out and try and recover by saying, ooh, I think you got your IP address wrong, or maybe you got your fully qualified domain name wrong, or something like that. So here's the server socket. Now, we've seen these in action too. These will sit down and they'll allow us to listen to a specific port. Excuse me. They'll allow us to listen to a specific port. And then when we hit the accept method, it causes a sudden stoppage to the primary thread of execution. And until that returns, it simply waits until somebody makes a connection. And then you will have to handle the socket by opening up an input stream and an output stream and proceeding to monitor what comes into the input stream and then respond appropriately. That's what they call a stop and wait protocol. No throughput occurs when you hit the accept. And if somebody, similarly, if you go into a web server and you want to get, you have to stop and wait until there's a return. So there's no throughput during the stop and wait phase of a network interaction. So server socket waits for requests to come in over the network. Once they come in, typically you launch a thread to service the requester. So the server socket work, it has to be done by some sort of a implementation class. It's called the socket implementation. And so that's a super class. And you can kind of see these things if you're interested. You can go to let's see if we can find a daytime server. So here's a socket. We can go to the socket implementation, and it implements closable. And closable is just an interface that says it can close. So when it's done, it'll close. You want these things to close. And so here's the socket implementation. And so what we see is that the socket actually is a wrapper for the socket implementation. So socket has a socket implementation in it. And now the socket implementation is this abstract class which implements the socket options. And then that interface has God knows how many options. And certainly they declare these variables as being final, but because they exist inside of an interface, they're all final by default, I think. Default? Anyway, by spec of the Java language. And so they declare them as final, but that's redundant. And there's a lot of different sort of options that can be set in through here. And so that's kind of an interesting anatomy. When you look at something like a socket delegating its methods through method forwarding to a socket implementation, what you see is a form of delegation. Delegation is an interesting way to do design of programs. And if you haven't seen it before, or if it's new to you, you should be aware of it. Delegation basically says, I don't want to get these methods by inheritance, but I don't want to rewrite the methods either. So I will method forward to all of the methods that are contained in the implementation, and then I'll wrapper them in a clean facade, which hides the complexity of how things are being implemented inside of the socket implementation. So socket is a kind of closable, implements closable, but socket has a socket implementation in it, and it methods forwards into that. So it serves as a delegation, right? So sockets implementations are delegated to the socket IMPL. And so you could call any one of the number of methods and just see things forwarded through. And then what you get to do is you get to wrapper the forwarding through things like a proxy. And that is another way in which you can get around firewalls. So if there's like a proxy forwarding system inside of Fairfield University, you have to know what that proxy is. You have to set it, and then you can't go directly to the internet. You have to go through the proxy, and it has to let you out. And that is a form of security. So you have to program for that form of security. And so that's one of the reasons why you do the implementation and you separate it with a wrapper, because you want to insert something like proxies in front of it. So that's a rather complex way to say you can't get out to the internet directly unless you go through the proxy firewall, which has been set up by, let's say, ITS. So here comes UDP. It's said to be unreliable, and in a sense, that's exactly right. It's as unreliable as the United States mail, right? You drop something in the mailbox, you don't know if it got there. You could create a protocol, return receipt, using registered mail, so that when it's signed for by the receiver, you get back a packet consisting of a postcard that says the package was received. Or you could put a tracking number on it, and you could use the tracking number to see if it's been received electronically. That's very similar to the way the UDP works, unless you have some mechanism which you impose on top of the UDP transmission to validate the fact that it was received. You have no way to know if anybody has gotten the UDP packet. Now, that can be to your advantage. If you're Netflix and you're streaming out movies to umpteen bazillion subscribers, there's going to be packets getting dropped all over the place. They're not necessarily critical. These are not mission critical packets because they consist of, let's say, some video. And if you drop a few video packets, your quality may suffer, but you're going to continue to be able to watch your video. So what they can do is they can use the unreliable packet transmission and flood local servers and not have to worry about packets being dropped. So that's kind of an interesting approach to multimedia transmission, because you have a lot of data in multimedia transmission that's not critical. So this means I don't have to set up a connection. Let's think about a real connection-oriented network, which has been around for over 100 years. It's the phone system, right? What do? Well, I set up my connection. I dial a number. The phone rings. Somebody answers it. I get a guaranteed quality of service. And it appears as though I have a virtual circuit to the other station, because I'm able to have it back and forth in real time. And there's relatively little latency in terms of when somebody talks and when I hear them. And similarly, when I talk and they hear me, there's relatively little latency. That used to be a solid circuit switch network, which meant that if you turned a crank on an old phone, a 90-volt generator would send a pulse down the line. And then an operator would see it ringing on her board, and she would plug in her headset. And since you didn't have a way to dial, all you could do was crank. So she would say, "What number, please?" And then you'd give them the name of the central office based on its location, Murray Hill, 723. And then she would say, "Just a minute." And she would plug you into a trunk, an outgoing line, physically with a jack. And she'd ring up the Murray Hill operator, use the 723 extension, and cause that to ring by sending a pulse down the line from the central office at Murray Hill. And then you would have ownership of the wire that went from your house, no more than 3 miles away from the central office, all the way through the trunk line at the central office to the other central office, and then to the other station. And that's how the phone system used to work, and it was all switched manually. Later, when they went to, I don't know, automate, for lack of a better term, the operator function, they basically turned all the users into operators, because the users ended up operating the stepper relays by using a rotary dial and later a touch tone system to make what is called today a virtual circuit switch network, which is now being replaced very rapidly by a voice over IP network. So that's the phone system. And now, I used to work for the phone company. I don't know what a phone company is. Isn't that weird? I don't know what a phone company is, right? Is Magic Jack a phone company? Because they give you phone services. How about the cable company? Are they a phone company? I think anybody with an app that runs on an iPhone that gives you the ability to talk, like Talkatone, they must be a phone company. So everybody's a phone company, and nobody's a phone company. I don't know. If I write an app that lets me talk to other people, I'm a phone company. No kidding. It's a bizarre turn of events. So here comes a datagram packet, right, which puts together the two different terms, and you throw in a unformatted sequence of bytes. Look, it's just an array of bytes. You give it the length out of this array that you're trying to transmit, and if you want, you can construct it with an internet address if you don't already have one set, and even a port. And so that allows you to go and take the datagram and drop it into the network. So it's kind of an interesting thing. It's not a hard API to learn. And let's see, what else do we need to know about all this? We can set the address, set the port, so we don't have to do it during the construction time or during the invocations for sending data. And so that's cool, right? Now we've got a way to send datagrams. And so I've got a datagram socket, which can take the datagram packet and send and receive datagram packets. The sockets are going to be bound to an address. And it turns out it's unreliable. I can have lost packets. And so timeouts are sort of important. And so here's the datagram socket. And I can set the timeout. So when I go to receive some kind of data, if I don't get any data coming in, I can time out on that. So Echo uses datagrams. Very typical. Let's do an echo. I could probably ping my router. And it tells me how long it takes to get there and back. And that small datagram packet is only 64 bytes long. So in principle, you can write your own little echo service. You could write it in any language you like. And then you could proceed to ping a network in order to check to see how long it takes to send a packet and have it returned. Here's an example of doing just that using UDP. We're going to use UDP to drop a datagram socket into place, throw a datagram packet with some byte array into it, and then send it out to that socket and see if we're going to get an answer back. And that allows me to do a little demo so you can see how this stuff works. Let's see if we can get in there and do that. I think I have a I think it's called MCast. So if I just do a quick find in path MCast, there's my little multicast utility. Let's see if we can find an example where this is used. I think there's a main method in here somewhere. If not, what we'll do is we'll see who uses it. Find usages. Yeah, I've done this with games. That's a good one. A multicast chat, that's a nice one too. So I'll try the multicast main. See if we can get that running. It's been a while. So here's a multicast main. And now what I'll do is I'll run it again. I don't want to stop and rerun. I want to start another one. It's not allowed to run in parallel. Why not? Really? Can't run in parallel? That doesn't sound good. Well, that's not good at all. Huh. Why won't he let me run it in parallel? Well, there should be a main method in here somewhere. Edit, find, main. Here it is. So I'll just run it twice then. Haha on them. Can't run it in parallel. So I'll run two of them. So there. I'll run it twice. Oh, he didn't like it. I would really like to get another info frame up in here so it can show you this is transmitting using a multicast packet and is receiving the text. This is hello world. So he's transmitting to himself right now. What you want is somebody else on the network with a different machine running the multicast receiver. But right now I've got just one running at this time, and he's not showing two. Probably because I have too many static variables in this class. Just unfortunate. Bad design. Oh well, life in the big city. But anyway, if you had one of these chat mains running and you were on my local area network, you'd be able to see that text as well. And it would be multicast to everybody on the network. Back when I was teaching this in a classroom, which had computers, everybody could run it, and then you would have an opportunity to see it work in action. So that's kind of an interesting piece of code. I think it's probably a little too much for me to explain this code. You guys are not that advanced with the Java code, and you haven't had a network programming course. But if you take my network programming course, we'll learn how to read this code, and we'll definitely get into it a little bit. So, in fact, what we do in network programming is we do multicast, multimedia, multi-threaded services. It's very multi-oriented. So that's my little shtick on UDP. Let's see what we can do with all this information that we've learned in order to try and attack homework number 9. I think that would be educational, because that is your next homework assignment, due next week. So let's take a look. We'll go into Blackboard. Oops. We'll look at the courses. Get into computer systems architecture. Look at the course content. And somewhere in here, it should say homework. And I think the one that's due today is this one, socket programming. And the one that we're going to have due next week is datagram programming, which basically is about multicast. And so what we'll do is we'll open up that and take a look at what we got. So Datagram protocol is one of the members of the Internet Protocol Suite. What do you think of that? Is that see if we can find somebody new. Avery, what do you think of that? Is that true or false, do you think? This is the part where I get to see if people are awake.
I'm probably going to be wrong, but is it true?
That is true. That is true. So when we think about the Internet Protocol Suite, it includes user datagram protocol as well as TCP/IP. So that is quite correct. Quite correct. And then let's see if we can get to the next question here. We'll get through a couple of these. UDP uses a simple connectionless communication model with a minimum of protocol mechanism. Minimum. What does that mean? A minimum protocol mechanism. How about we think about this? I guess a minimum of protocol means no acknowledgments or something like this. So what would that mean? Would that be true or false, do you think? Who shall we call on? Caroline, you're my next.
Is it true?
Yeah, that is also true. So you guys are getting it. It sounds like you've been paying attention or something. Look out, there may be some learning going on here. Uh-oh. Let's see now. What's my next question? Serialization. All right, so this we didn't really cover yet, and that needs a little bit more treatment. Serialization. Does anybody know what serialization is? Serialization. To learn about serialization is to learn about the next logical step in object-oriented distributed computing. That's sort of an interesting statement, actually. Let's take a look and see if we can get what I'm looking for here is a nice lecture on remote method invocation, which would be chapter 43. This is out of the Java for Programmers book. And remote method invocation gives us the ability to, just a moment while I change my aspect ratio because this is not working. Scale. Ta-da. Fills the screen. So remote method invocation allows us to take objects and invoke them from another machine, completely unrelated to the first machine, except by virtue of the fact that they know each other's interfaces. And so I have a mechanism now to create an architecture for a cluster of machines that can do computation for each other, a kind of peer-to-peer computation. And so what we see in RMI protocol is we have a client and we use an RMI server, which goes to a registry on some remote host and tells us about where other services may be available. That is to say, the RMI registry is a service which tells us about other RMI servers. Using that registry, we can then proceed to register those other servers, look them up, and then make use of their services. So lookup services are the kind of thing you would expect from a domain name server, right? Domain name server takes a fully qualified domain name, gives you an IP address. This takes the name of a compute service and then provides some machine that provides that service. And so what you're doing is you're providing what's called a substrate, right? Substrate is a layer, and it goes on top of another layer, and you might even call this a presentation layer, because what you're doing is you're running on top of the transport layer, which runs on top of the network layer, which runs on top of the data link layer, which runs on top of the physical layer. And what it does is it enables you to go beyond the unformatted sequence of bytes that you get from a stream and start to pass what's called serialized instances of objects. So this is an interesting way to obtain persistence and to obtain remote computing. A serialized instance of an object takes an instance and turns it into a sequence of bytes. And that's it. That's what serialization does. So if I make an instance of the payroll, I can take that instance and I can save it to a file. But an instance is to a class what a cookie is to a cookie cutter, right? One cookie cutter can make many, many cookies. One class can make many, many instances. And if you want to deserialize an instance that's been saved to a file, you must restore it to a class that has not been modified since the instance was saved. This is so important because it makes instances rather fragile when they get saved, because persistence only works when the classes that created the instances that got serialized remain unchanged. As soon as you add a new variable or a new method or a new subclass or a new interface, you've broken the shape of the cookie cutter, and the cookies will no longer fit back into the cookie cutter. You've broken persistence. So what you need to do is you have to have a consistent class that's being used for the serialization process. So what happens there is not only is the instance being transmitted, but all of the arguments to the method that the instance is trying to invoke have to be marshaled. Those parameters are serialized and sent over the network when remote method invocations are made. Or else you would not be able to communicate the instance invocation to the receiver. So serialization is so important, not just for distributed computing architectures, but also because you want to be able to save instances to a file. If you want to save payroll and you don't want to have a special ASCII format for payroll, like comma separated values that you have to parse later, then basically you want to take the instance data structure and you want to stream it. You want to stream it out to a file output stream. That's a fairly routine thing to do. Here's some student data. Apparently, students know that they have a grade, an address, maybe a shoe size, some room where they sit in, their IQ. We like to have that too. We have complete files on everyone. So then there are these things which will be saved when we serialize the student data instance. And then there are these things that will not be saved, such as the name. They are declared as transient. Those transient elements do not get serialized. The serializable interface is implemented by all classes that we seek to save. And so when we look at all of the getters and the setters, if you were to change any of these things, you would break serialization. And here's a tester for the read. And what he does is he gets a file and then he makes a new instance of a file input stream. And he takes that file input stream and he passes it as an argument to the object input stream, which deserializes the data that's in that file and puts it into this object input stream instance from which he can do a read object. And because student data instances know how to convert themselves into a string, we can print the instance and it will print out properly. So the instance already knows how to convert itself into a string because we've overridden the toString method. ToString is a method that's part of the java.lang .object. So before we test a read, we'd better test the write and write out the student instance to a file. Let's see if that works. So he wants to know where it gets written. And what we'll do is we'll write it to attachments. Just a minute. Attachments, open. Oh, it's not letting me do that? Really? Test write. Get read file. Get file for output stream. Well, let's just throw in a new file. New file. Slash home lion attachments slash student data.ser. We'll just say .txt. I think that's perfectly fine. So let's write that and we'll look to see if that got done. Done. So presumably we should now be able to go into attachments, look at student data.txt, and we can see what was being written. And what we see is the fully qualified name of the data, book examples, chapter 15 streams, some binary stuff, which we don't know how to read. This looks like some strings and some other things. There's the shoe size. It's all in there, but it's in some gobbledygook form we can't read. And so now what we want to do is see if we can decode from the serialized instance, which I have hard coded. This is not best practice, but I'm doing this because my file read procedure somehow didn't work. And so what we'll do is we'll do a test read from the same place. And we'll call test read from our main method and comment out test write and see what happens when we try to restore the data. And so we got the name as null because that's transient, and the grade apparently was set at 100, which, yep, set grade 100. Set name, which is transient, J Schmo. That could be Jane Schmo or Joe Schmo. We don't know. So it's an equal opportunity Schmo. And that enables us to effectively serialize the instance. And this can be as complicated as you like. If it's a student payroll, maybe you have all the students on the payroll all get serialized. So being able to serialize is so important if you're trying to have persistence with your data. It's also important if you're trying to do distributed computing. And the best way to do that is you implement serializable, you create an object output stream, and then you write the object out. So here's the object output stream, and there's the write the object out part. So when you're using, we'll call it distributed computing as part of your architecture, you start to think about doing object-oriented programming like this. And that enables you to have access to a lot of different computers on the network. The stubs are just mechanisms of interface so that you can know how the serialization is going to be formatted when it is transmitted. In other words, what it does is it gives you semantics on top of the syntax so that the compiler can see how to reinstate the objects as it gets passed from one side of the network to the other. So this brings us to a question of how you can take a complex set of algorithmic formulas and break them down into a distributed computing system, right? So if you're thinking about how do I parallelize, let's say, an expression, y equals mx plus b, the well-known implicit formula for a line, right? So I think about it and I create what's called a parse tree for that. The parse tree says, I think I can get a, I'm going to try to draw a marker here. Here's my pen. So I've got times, and I'm going to draw times, and times has an argument, right? The argument is m. Boy, do I hate drawing with a mouse. And it's going to be x, right? And somewhere in here, there's plus, right? And that depends on times, which can be computed separately. And then there's b, which can be obtained separately. This is a standard parse tree. And so what we would do is you break down the equation into subparts that get computed first, and you dispatch those parts. So if m times x is a non-trivial thing, like they're both images or something like that, you can have that done on a different computer, provided the overhead of transmitting those images to the computer doesn't exceed the amount of time it takes to do the computation. If the amount of time it takes to transmit the data to the computer is higher than the amount of time it takes to do the computation, then your system becomes I/O bound and rather inefficient. So you have to kind of try to become CPU bound when you dispatch a parallel program over a network, because you need the CPUs to stay busy. So you have your compute client, and then you have your compute server. You've got your registry interface, so that's over in here. The skeleton, which may have some implementations that you need to use, and then some RMI registry, which runs so that your client can look up servers and proceed to do invocations. And I don't know that we're going to have time to do an RMI example, but I can say that these things are fairly well documented, and we can have a chance to do that if you want to take the computer network programming class. You'll start an RMI registry, we'll run an RMI compiler, and we'll start to do invocations remotely. And that'll be great fun, because then you'll be able to do distributed computing across a network of computers. There are a few different requirements that you have to comply with if you want to start using the RMI framework. One of which is that you have to subclass the remote class in order to be able to inherit certain classes from it. That enables remote invocation. And so what that means is you often are wrappering. That is, you have a has-a relationship with a number of the objects that it is you want to invoke remotely. You will wrapper those objects so that they will have remote object types, so that they will throw remote extensions, and so that they will become, I'll say, distributed computing friendly. So to make a class, a plain old Java object, or POJO as it's sometimes called, into a remote object usually requires a little bit of work. You've got to wrapper the class and do method forwarding into the instance that has all of the methods that you intend to invoke on the compute server. So this is a, I would say, the bird's eye lowdown on the RMI caper, whatever that means. We don't have much time because, as I look at it, we're out of time. But I did want you to have a sense of how to do this kind of distributed computing. Stay safe, enjoy the rest of the day, and thank you for your attention.
Thank you, Professor.
Thank
Thanks,
you.
Thank you. Thank
Thank
you.
you.